everyone. This is Dr. Sirisha working as Associate Professor in Institute of Aeronautical Engineering College. Today I am going to give you a brief introduction on B trees. What a B tree is, how we perform search, insertion and deletion operations on these trees. We are going to look deep into it. Okay, let's start with the session. Okay, let's start with M-way search trees. What is a M-way tree? It is a short form of multi-way search trees and it is of order M. M decides the number of children it can hold. Then why these M-way search trees have come into the picture? Let's talk about what basically a tree looks like. A tree, when implemented with a linked list, is a node which consists of three parts, a data part and two address points, where these two addresses are going to hold the address of left child as well as right child. So the amount of memory required to store such a binary tree is too high. Right? Because most of the memory is used to store the addresses of its children itself rather than storing the data. To overcome this wastage of memory, M-way search trees have come into the picture. In M-way search trees, that is the multi-way search trees, they'll be based upon the order. That is the order, say M. Then M denotes the number of children it can hold, right? And in between that, you have the actual data pieces. Have a look at the picture which I have given over here. It is a M-way search tree of order 8, right? It is having 8 children and it is going to hold 7 keys. That is, if there are M children, M minus 1 number of keys it can hold. And coming to the nature of these keys. In binary search trees, we know that for every node from the root to non-leaf nodes, all the non-leaf nodes, the left child will have a value which is less than its parent or less than equal to its parent, whereas the right child is having a value which is greater than its parent, right? So even the same funda is carry forward in case of M-way search trees also. Have a look at this figure which I have given over here. So in this picture, I have shown you a node with 8 children which is going to hold 7 keys. And these 7 keys, they are placed in ascending order. That means the value of K1 is less than K2, the value of K2 is less than K3 and so on. So that means the largest value in that node will be K7. So coming to the left and right children of these keys. The left children of a key will have a value less than or equal to that key and the right children will have a value greater than the key. So this is the nature of a multi-way search tree and how it works, right? So a variation of that is a B tree. It is a self-balanced search tree. So it is a multi-way search tree, which few add-on properties. If we keep on inserting higher values and higher values and higher values, the length or the height of our multi-way search tree goes down the lane in the right side only. It is not a balanced one. Right? So if the values we are inserting are less than the least value, keep on if we do the same operation, then the length of or height of the left subtree goes on increasing, even that unbalances it. To overcome that or to balance it, B trees have come into the picture. They are self-balanced search trees. So they are having few add-on properties when compared to your M-way search trees. They're also known as height balanced M-way search trees. Let's have a look at the properties. The first property tells that all the nodes must be at the same level. Leaf nodes especially. That means all the leaf nodes must be at the same level. That is the primary point, guys, which you need to remember. Second property coming to this one, all nodes except the root must have at least M by 2 minus 1 keys and a maximum of M minus 1 keys. The count of keys is also important. Third property, all leaf nodes, non-leaf nodes except the root right? Except the root must have at least m by 2 children. The root node at times bears only one child. Okay, and so on the remaining properties. It must have at least 2 children, all the non-leaf nodes, n minus 1 keys for n number of children, and the key values must be in ascending order. The last 3 properties are these properties of a multi-way search tree. Okay, let's have a look into the applications of B trees, where we use these B trees. They reduce the reads made on the disk, the reading, whatever the read operation, the amount of time which is required to read is reduced when we work with or we store the data in B trees, right? So easily optimize it to adjust in size, and there are design techniques for handling a bulk amount of data. As I said, as all the leaf nodes will be found at the same level, searching will be quite easy when compared to the remaining trees like binary search trees and your binary trees. Any tree you take, B trees are much beneficial, and they are mostly used in storing databases and maintaining file systems. It is a good choice to opt when you come to reading and writing a large or huge bulk of data. The areas wherever you use large data, say weather reports or earthquake reports, all these kind of things, the B trees will be used to store the data. Okay, so have a look a small example of B tree of order 4. So what does order tell us? As I already mentioned, order tells us about the number of children it can hold. So the number of children it can hold is 4, and the number of keys is 3. That is 1 less than the order. Okay, so that means the 3 data values each node can hold. Have a look at this picture and try to understand this one, guys. The root node is having, the root node is having 2 keys, and right now it is having 2 keys, and max it can have 3 keys, right? Max it can have 3 keys, and it is having 3 children right now. Okay, this is the current scenario I'm talking about. Okay, coming to the left children of 30. All the values 8 and 25 both are less than 30. Coming to the right children of 30, which are 40 and 50, both are greater than 30. Okay, this is in the point of view of 30. Coming to the key value 70. In view of 70, its left child is having values 40 and 50, which are less than 70, and its right children are 76 and 88, which is greater than 70. Okay, so by this you can understand that for every key, its left children have values which are less than itself, whereas right children are greater than itself. Okay, let me give one more example. Let's take the middle one. Okay, have a look at this one, guys, keenly. Okay, 40 and 50 are the 2 keys you have. The left subtree of 40 is bearing the values 35 and 38, which is less than 40, whereas the right subtree of 40 is 42 and 49, which are greater than 40, right? So here the property of searching is prevailed. Coming to the left subtree of 50, which is having 42 and 49, which are less than 50, and right subtree of 50 are having 56 and 67, which are greater than 50. Even here the search property is prevailed. This is how, and you can observe basically all the children are at the same level. All the leaf nodes are at the same level. These are the basic properties of B trees which are shown in this given picture. Okay, So what are the basic operations that we can perform on B trees? One is search, second is insertion, third is deletion. The complexity of all the three operations is order of log n. Okay, let's start with one by one operation. Searching. This is an algorithm to perform search operation. So whenever a value is given to you, a key value is given to you to search for, first of all, searching money, we are trying to check whether it is present in the B tree or not. If it is present, where it is. If it is not present, just to display that the element is not found, right? So that is the basic search operation we generally do, right? So first of all, whatever the search keyword, first key value which you want, first compare it with the root. Read that key and compare it with the root. If it is a match, then go for the step 3, node is found, and terminate the function. If it is not found, then check whether the key value which you are searching for is having a value which is less than the root or not. If it is less than the root, perform the same operation in the left side. If it is greater than the root, perform the same operation on its right. So you need to just decide in which direction you need to move in each and every step. If the element which you are searching for is not present in the node and it is less than the node, then go to the left hand direction. If it is greater than the node, go to the right hand direction. Okay, so once you reach a leaf node and still the element is not found, then you can simply display saying that element is not found and terminate the function. Okay, this is the basic search operation which we have. Coming to the insertion operation. Okay, have a look at this algorithm which I have given. And please make a note that we can add only leaf nodes. We can add only leaf nodes to any B tree. The new node is going to come and settle as a leaf node. Very good. Let's start the process. Check whether the tree is empty or not. If it is empty, then whatever the value which you want to insert will become automatically the root node, right? So a single node. Coming to the step 2, if the tree is not empty, then create a node with a new key and insert into the tree as a root node, right? So if it is not empty, then find a suitable leaf node space where you can fit it. Okay, so for this one, we need to go with step number 4, 5 and 6. If the leaf node has an empty space, then insert it in ascending order. If the leaf node is not having an empty space, then take the middle value and push it in the upward direction. And that means take the middle value and place it beside its parent. If the parent block is full, then in the parent section, take the middle value and send it to its grandparent section. Don't worry guys, I'll explain you with an example, 2 examples. I'm going to explain how this happens. So if this splitting is performed at the root node, then the middle value becomes the new root node and the height of the tree increases by 1. Okay, let me explain you the same with an example. Let's look at this picture. I'm trying to construct a B tree of order 3. Order 3 means what? It will have max 3 children and 2 key values max. Right? And I'm trying to construct a B tree of order 3 for the values 1 to 10. That means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So initially I have taken a node. Okay? It is empty basically. I inserted 1. There is no computation, nothing to check. I have inserted 1. Then inserting of 2. In that node, there is an empty space, right? And as I said, we have to insert them in ascending order. 2 is going to sit right of 1, right? Then coming to 3. When you come to insert 3, as the node cannot accommodate 3, the middle value 2 is going to go to its parent section. Okay, and it becomes the new parent of 1 and 3. Have a look at this one. 2 became the parent of 1 and 3, where as 1 is a value less than 2 will become the left child of 2. 3 is greater than 2 will become the right child of 2. Now, what will happen if you try to insert 4? As a 4, as I said, all the new values or keys are going to set or select a position as a leaf node only. Okay, so 4, where 4 can sit? Beside 3, because 4 is greater than 3. Can this node accommodate 4? Yes, it can accommodate. Job done. Fair enough. Right? Coming to 5. Just give a try, guys. What will happen if you insert 5? 5 is supposed to sit after 4. But can this node accommodate? No. What is the middle value? 4. Send it to the parent section. Can parents accommodate 4? Yes. There is a space beside 4. Then 4 is going to come and sit beside 2 on the right hand side of 2. Have a look at this picture. Beautifully drawn. So 2 and 4 will be the new root, whereas 1 is the left of 2, 3 is the right of 2. Coming to the in view of 4, 3 is left of 4 and 5 is right of 4. Right? Now, what is the next element that is supposed to be inserted? 6. So, it is going to sit beside 5. Is there any problem? As that node can accommodate, no problem, insert it. Job done. Now, you have to insert 7. This is the right position of 7. Can this node accommodate 7? No, it cannot accommodate. Then, what you are supposed to do, you are going to set 6 to its parent section. So, 2, 4, 6 is the right order. But can the root node accommodate? No. What is the middle value? 4. Send it to the root. I'll show all these things pictorially. Have a look. 7, due to 7, 6 took a hop in the upward direction. Due to 6, 4 took a hop in the upward direction. And this is the final result of insertion of 7. Okay, have a look at this one. Check at all the intermediate stages. Please check whether your search property is prevailing or not. Okay, so 1 is less than 2, 3 is greater than 2. Very good. Coming to 4, 1, 2 and 3 are less than 4. Left side property is prevailing. Coming to the right side property, 5, 6, 7 are greater than 4. Even this property is prevailing, not a problem. Okay. Now, insert 8. Not a problem. Besides 7, right hand side of 7, 8 can sit. What if you want to insert 9? That is the next point. 9 cannot be accommodated in this node. So 8 is going to take a hop in the upward direction. And the parent is having a vacancy and it can accommodate it. Right? So 8 is going to sit beside 6. No problem. Coming to 10, simply insert it beside 9. Okay? So no clashes, nothing. Have a keen look at this picture. Guys, you don't have any problem. The search property is prevailing. Okay, so this was an insertion operation, or you can say construction of a B tree of order 3, right? If an ascending set of data is given. What about a B tree if a shuffled set of values are given to you? So let's have a look at a second example, which will give a demonstration for the same. Okay, so let's have a look. This is an envisaged tree. The question is given. Have a look at the list of the values which I have chosen. 5, 3, 21, 9, 1, 13, 2, 7, 10, 12, 4, 8. Random values I have taken of order 4. What do you mean by order 4? How many children you are going to have? each node will have 4 children. So 1, 2, 3, and 4. It can have 4 children. How many key values it can have? It can have 3 key values. And what should be the nature of these 3 key values? Say K1, K2 and K3. What must be the nature? K1 must be less than K2 and K2 must be less than K3. Right? So please keep these points in your mind and let's start constructing. So initially a node was empty. I was supposed to insert 5. So I have inserted in the empty node and it is acting like a root now. Now the next element to be inserted is 3. When I am supposed to insert 3, as I just now said, the keys must be in ascending order. So I have moved 5 to the right and gave a space for 3 because 3 is less than 5. Right? Next 21. Yes, it can be accommodated in this node as a right person to 5. Now you can see the property 3 less than 5 less than 21. The basic properties prevailing. Okay. Now let's have a look at insertion of the remaining elements. What if you try to insert 9? What is the right position of 9? You guys tell me. So if you place it in order, 3, 5, 9 and 21 is the right order. But can this node accommodate 9? It cannot accommodate 9. So what is the middle element? Being 9, taking 9 as the middle element, the ceiling value, I'm going to send it to the top. When I send it to the top, all the elements left will become the left subtree and right elements will become the right subtree of 9. Let's have a look at this picture. I hope you understood. Each and every node will be of order 4, guys. Even if it is having single element also, it will be of order 4. Okay. So you can see the such properties prevailing. Okay. So 3 and 5 are less than 9, whereas 21 is greater than 9. Okay. Very good. Next, what is the next value which you have to insert, which is 1. 1 is the smallest value till now, right? So it is supposed to come left to 3. So yes, this node is having an empty space, so you can shift the values. So I have shift 3 and 5 took a hop and gave a space for 1 and 1 is sitting over here. Right? Now this node is full. Please have a look at this one. This node is full. All the 3 keys are present. 1, 3, 5. 1 is less than 3 and 3 is less than 3. Right? Next element to be inserted is 13. Right? So 13 as it is greater than 9, it is going to sit in the right subtree of 9. Right subtree already 21 is there and empty space is also there. So 21 is going to take a hop and 13 is going to sit. Right? So job done. Next element to be inserted is 2. So what should be the right position? 1 order. I will say 1, 2, 3, 5 is the right order. And we fix it to the point that mid element will be taking the ceiling value. Okay. So ceiling value means 3 will be the middle value. So 3 will be set to the top. So where 3 is going to go to the parent, where that means it's going to 9. So once it goes to 9, what will happen? Once it goes to 9, as 3 is less than 9, 9 is going to take a hop and give a space for 3. Right? So the left of 3 are 1 and 2. Right of 3 is 5. Have a look at this picture. So this will be the left subtree of 3. This will be the right subtree. Right? Have you seen this one in diagram? So the right of 9 will be as it is. Have a look. With this division, we can say that 3 and 9 and their intermediate value is 5, which is sitting between them. So the such property is prevailing. Okay. What is the next element to be inserted? 7. 7 is greater than 3, whereas less than 9. That means it is going to go to a child which is right to 3 as well as left to 9, right? So, and this node have some vacancy cells are there, vacant cells are there. We are going to place 7 in the ascending order. Okay, right. What is the next element to be inserted? 10, which is greater than 9. Mane, it is going to go to the right child of 9. Right child of 9, already 13 and 21 are there. They are going to take a hop, and 10 will be getting a 2 space, right? Next insertion will be 12. What is the right order? 10, 12, 13 and 21 is the right order. But the node cannot accommodate 4 key values. Its order is 4. So 3 key values only it can hold. So 13 is going to reach the top, making 10 and 12 to be its left children and 21 to be its right child. Okay? Let's have a look at this one, my dears. So once I'm going to send 13 to the top, this is how it is going to look like. Right? So 13 went to the top and the right child of 13 is 21. Have a look at and search for the search property over here. So 5 and 7 between 3 and 9. Very good. 10 and 12 between 9 and 13. Very good. Right? Job done. So now it is a point of insertion of 4. Where 4 can go? It is a value which is greater than 3 but less than 9. So it is going to become the right child of 3 or the left child of 9. So can a node accommodate it? Yes, it can accommodate. There is a vacant space, right? So shift 4, 5 and 7 and give space for 4. So this is how we are going to construct a binary search tree for any given order. Okay. So next, if you try to insert 8. Okay. So the 8 value is between 3 and 9. But the between cell is not having any vacant space. What you are going to do? You are going to send the middle value to its parent. That is 7 is going to travel in the upward direction. So if it travels into the upward direction, the order will be 3, 7, 9 and 13. But even the root cannot accommodate it. What is the middle value? 9. 9 is going to become the new root. 9 is going to become the new root of our tree. So 9 is going to become the new root and its left children are 3, 7. Right is 13. Left of 3 is 1, 2. Right of 3 is 4, 5. Or left of 7 is also 4, 5. You can say it in either way. They both refer to the same node. And right of 7 is 8. Left of 13 is 10, 12. Right of 13 is 20. So this is how you can see that all the leaf nodes. So while drawing, I couldn't show it well, but have a look at the level. They all are at level 2. All the leaf nodes are at same level. Okay. This is how we are going to insert elements into a B tree. Now let's have a look at the deletion operation. How to delete. Inserted, we gave vacant space and we made it if space is not provided, we send the middle element to the top. But deletion, how we are going to do? We need to follow few rules. At every point of time, with each and every deletion, the resultant tree must abide to the rules of multi-way search trees, right? So have a look at the algorithm, right? So locate the leaf node, the element which you want to delete. If there are more than m by 2 keys in the leaf node, then delete the desired key. Not a problem. If there are 3 elements, you delete 1 out of the 3 keys, max 3 keys, then there will not be any problem because 2 keys will be present, which is greater than half. Right? What if removal brings it down? So either one of the siblings, left or right siblings, you have to sacrifice. So 2 options will be there. If the left sibling contains more than n by 2 values, then push its largest value to the top. If its right, that is the right sibling is containing more than employee values, then push its smallest value to the parent. Okay, I'll show you everything pictorially. You need not worry about that. Okay, so if neither of the children can help you because removal will bring them down, then create a new leaf. New node joining two leaf nodes and intervening element at the parent. Okay, so last category, if the parent is left with m by 2 nodes, that is the last hopeless case, apply the above process to the parent. Okay, if removal brings that down. So if the node which is to be deleted is an internal node, then replace the node in its in order successor or predecessor. I hope you know that in order traversal of multi-way search trees, that is B trees, will give you a list in ascending order, list of the data in ascending order. So you can use either the successor or predecessor. Okay, right. Have a look at this tree. Let's have a look at this tree. On this, we are going to perform deletion operations, and I'll explain how it works. Okay, so make a clear picture. Have a look at this one. So on the right hand side of 50, all the values are greater than 50. All the values on the left side of 50 are smaller than 50. The same with the remaining things also. And all the leaf nodes are at the same level. Okay, it clearly depicts a B tree. Can you tell me the order of it? So order is 3 because it can have at max 3 children. The number of keys, 2 keys. If order is m, then number of keys will be m minus 1. Okay, so let's delete 65. So if you delete 65, no problem. 50% of the data is there, no issues. What if you delete 70? So I have to merge them. So I have merged. Have a look at this previous picture. What if you delete your value 70? Then the 90 is the only element which is left in the node. So I'm going to merge two nodes, 60 and 80 and 100. So as 90 cannot have 3 children, at max it can have a right child and a left child. That's it, right? So 60, 80 and 100, they cannot sustain. So I've merged 60 and 80 into a single node. Okay. Now have a look. What if I remove 100? Not a problem. 80 will go to the top and 90 is going to come to the bottom. Why? Because previously 90 was on the top and 60 and your 80 were at the bottom and 100 was here. Right? If you remove this one, what about the right child of 90? Imbalanced, right? To overcome that, what I have done is I brought 80, I made 80 to be the parent and 90 to be the right child of 80. Okay, the same picture is shown over here. To balance it, what did I tell you? 50% must be there, right? So, what if I remove 80? No problem. 60 is right child. Bring, that means you have removed the root, right? The right root of the right subtree. If you remove it, no problem. Nothing is going to happen. Don't get panicked. Just move 60 to the top so that if the root place is gone, one of the child must occupy that space, right? Inheritance, property of inheritance. Next, let's have a look at another example. This is the final one which we got in our previous example, right? Have a look at this one. What if I remove 6? Comfortably I can remove, no problem. 4, 5, 6 was over here, right? I removed it, no problem. 4 and 5 are there to balance. What if I remove 12? No problem. 10 and 11 are there, balanced. What if I remove 7? If you want to remove 7, this one. Now the point starts. You need to replace it, right? So one second. We need to replace it. We need to replace it with either 4 or that. Sorry, you need to replace it with either 5 or 10. Anyone is going to prevail. What they say? Successor or predecessor, right? Its predecessor will be 5, whereas successor will be 10. If you replace the position with either one of them, problem solved. Okay, this is how we are going to delete an element in a B tree. So we have gone through the, please let us recollect whatever the things which we have seen in this session. Basically, what is a multi-way search tree and what is a B tree, how we perform search, insertion and deletion operations on B trees, and what are the applications of B trees. I hope this session was good, and if you have any queries, please post this. Thank you. There ends with we have seen how we delete the elements in an MV tree or binary tree B trees, right? So order 4 you have seen over here, 4 children maximum it can accommodate, right? Then coming to the applications, as we have seen, B trees can be applied in the cases where you have abundant data, huge data, but there will be cases where you store data in warehouses where terabytes of data is used, in those cases we cannot use even B trees, these multi-way search trees, to store the data. In such applications, red trees comes into the picture. Yes, there are many trees, many types of trees in this world that are being used to store the data. So basically what we have learned till date, what is a tree, then what is a binary tree which has only 2 children, then we have seen what a BS tree, then we have seen what an AVL tree is, then we came to our multi-way trees, that is M-way trees, thereby we came to our B trees into the picture. Okay, so this is a hierarchy of all the trees that we have learned till date and which I have explained in my previous videos. In the coming videos, in case of all these non-linear data structures, I'll be explaining you about what a graph is, how it is represented, and in what are the different ways with which we can represent a graph, right? And then what are the graph traversal techniques, right? All these things we are going to cover in the coming videos. And guys, if you have any doubts or queries coming your way, please let me know. Post your reviews in your comment section, and please do help us to refine our talks. I hope this lecture was fine and you were able to understand it. And thank you. Thanks a lot.
share and subscribe. Hit the bell icon for more updates.